I think I wanted to be an astronaut. And I'm not sure how I got into that, but somehow maybe it was watching Apollo landing on the moon or something that got me there. But I just remember thinking that's what I wanted to be. Then I went from there to aeronautical engineer. And then from aeronautical engineer, I ended up doing electrical engineering.
That was Praful, our guest for this week on Technology Now, telling me all about what he wants to be when he grew up.
I love that he wanted to be an astronaut. I was far less ambitious. I just wanted to be a veterinarian.
Ooh, that's not less ambitious, Sam. That's very impressive. What's your favourite animal?
Well, growing up as a kid, it was tigers. And I remember watching an animal documentary, and that's why I wanted to be a veterinarian.
Nice. Well, I wanted to be a train driver. I'm still holding on to that ambition. Maybe maybe I should have a side hustle as a train driver. I think I'm still sort of into trains, but anyway, that's an episode for another time, maybe another podcast. Anyway, Praful is not an astronaut, but he does something equally as cool because he's now the VP of Product Data Center Platforms and AI Solutions at HP Networking. Now, networking, especially in the context of AI, is what we're talking about today on Technology Now. So let's start the show. I'm Michael Bird.
I'm Sam Jarrell.
And welcome to Technology Now from HPE. So, Sam, I want to very quickly draw a line between two quite similar sounding topics. It certainly has had me confused a couple of times. Networking for AI and AI for networks.
Okay, that sounds like a riddle. What is the difference?
It's not a riddle. Okay, so AI for networks is where we use AI to help manage our existing networks. Whereas networking for AI, which is what we are covering on today's episode, is all about how we can build networks which can cope with a modern AI workload. Does that make sense?
Yeah, I think so. And I assume that would be because networks running AI need to be able to handle bigger workloads and that sort of thing, right?
Yeah, exactly. And that's why I spoke to Praful, who you heard at the top of the episode. Now Praful's background in networking and AI makes him the perfect person to give us a bit more insight into how AI networks have had to change to keep up with a modern demand for AI.
Okay, that does sound fascinating, but I want to take a moment before we chat to Praful about modern networks to look back at a much older network standard that has somehow withstood the test of time, which means it's time for Technology Then. Okay, Michael, if I say the names Bob Metcalfe and David Boggs to you, maybe throw in the year 1973 as a hint, do you think you can guess what I'm talking about today?
I mean, something to do with networking, but yeah. I don't know their names.
Well, Metcalfe and Boggs are actually the inventors of Ethernet.
Ah,
yeah.
Okay.
And I'm sure back in 1973, they had no idea that 50 plus years down the line, this protocol would still be the dominant wired networking technology across the world. So, how did Ethernet work? Well, back in the day, Ethernet used a coaxial copper cable, the sort of cable which can still be used to plug an aerial into your TV to transmit signals, and the signals were transmitted using rules governed by the Ethernet protocols, which both the sender and receiver would have to have had understanding of. The message would be split into frames, which would have to include the destination for the frame to be sent and the source's address, along with ensuring the frames were neither too big nor too small. Think of it as trying to send a book in the mail, but you have to send it a chapter at a time, with each chapter being posted in a letter addressed to the recipient with your return sender address on the back. So the reason the delivery address is so important is that the letter would be delivered to every single computer attached to the Ethernet, all of them. And the computers would have to check if the message was actually intended for them or for someone else. Now, the problem can arise when lots of people are connected to the same network, because if you all want to send messages, they could start to interfere with each other, like everyone talking at the same time. But Ethernet has a simple solution for that too, although it is a little bit wordy. It's called the Carrier Sense Multiple Access with Collision Detection.
Really rolls off the tongue, doesn't it?
Yeah, exactly. And it's a long name for a very simple concept. If you want to send a message, the computer will check to make sure no one else is sending messages before it transmits. It's like, when you have a big conversation with a lot of people, one person gets the magic talking stick. It's the computer equivalent for waiting for someone else to finish before you start talking. And if two computers try to transmit at the same time, they recognize there's been a collision of messages, and then they wait a randomized length of time before trying again to avoid the same thing happening twice. Pretty cool, right? There is, of course, more to Ethernet and how it's transformed to meet the needs of the modern world. Modern Ethernet used in networking for AI is point-to-point, which avoids issues like collision, and I have no doubt we will come back to this in a future episode. But for now, I think it's pretty cool to think about this technology, which is still fully backwards compatible, all the way back to where it started over 50 years ago, still being one of the most vital protocols in modern society.
Yeah, absolutely. And actually, Ethernet is something which I did briefly chat about with our guest this week, Praful Lalchandani. He is VP of Product Management at HP Networking, and he started by giving me an overview of how he got to where he is today.
So I started with Juniper 2015, but along the way, I started to think that networking was getting a little bit boring. Everything was moving to the cloud. So I had an itch to do some startups. So I went and joined one startup. It turned out that startup got acquired back into Juniper. But then my startup itch was not really over, so I joined another one, which was in the edge compute space. Again, wanted to do something small, so do something differently. That company actually went bankrupt. So I was out there in the market looking for a job. And my boss from my first startup, who was still at Juniper, reached out to me and said, networking is becoming sexy again. There's all this AI infrastructure build out that is happening. And, things are moving fast, technology is innovating fast. There's a lot of business to be made over here. So really excited to be here.
What is it about networking in particular that excites you?
It's the fact that it enables AI the way it does. You obviously think of GPUs. GPUs are the enablers for AI. But, whether you're looking at AI job training, which requires thousands and thousands of GPUs, essentially, it's a distributed computing problem. And that distributed computing problem needs the network, because if you are a cloud provider or an enterprise spending hundreds of millions of dollars on your AI infrastructure, which is mostly GPUs, you don't want the network to slow it down. So the thing that got me excited about networking was that networking became important for enabling this AI infrastructure. And frankly, I had seen speeds 25 gig going to 100 gig very, very slow. And suddenly the last 2-3 years has gone from 400 gig to 800 gig and now to 1.6T. So technology is evolving fast. The needs are evolving fast. And that's kind of keeps it exciting.
So before we sort of dive into the questions, can we just start by clarifying a couple of terms that I've started hearing more of? So scale out, scale across, and scale ups. What exactly do we mean by that?
Yeah, so good question. So if you think of a AI cluster, there are racks of GPUs. So all the networking that happens within the rack is called a scale-up networking. Essentially, all the interconnect within the rack between the GPUs treat each other as a single unified memory address space over which they can do load store operations, right? Now, one rack is not going to be enough. You generally have to do training across thousands of GPUs, maybe hundreds of racks. And you need a network that connects all of these racks together. And that's what is called scale-out networking. And Michael, one of the things that everybody who's building AI clusters is soon realizing is what's the biggest constraint in your data center? It doesn't tend to be space. It then ends up being power. Your power is your restraining or constraining factor of how many GPUs can you deploy in a single location. So what ends up happening is that these cloud providers are building multiple data centers that are 10, 20 kilometers away. And that's where scale across networking comes into the picture, because you want to be able to deploy that training job across multiple GPUs that don't fit into a single location, but now you need networking across those locations. And that is called scale across networking.
And I guess with each of those levels, there are different challenges and different ways of solving those challenges.
Oh, absolutely. So scale up networking, more bandwidth per GPU, but it's all within the same rack. So it can all be copper. Copper is going to be cheaper than fiber any day of the week. But if you're using copper, you need to be really, really sure that the signal integrity between your GPU and the switch is really solid. So there are those kind of challenges out there. When you scale out, you have a leaf spine fabric. And the two technologies that are at play over here, but obviously coming from a Juniper side of the world, we are looking more at open standard Ethernet technologies to enable that scale out fabric. And the challenge over there is mostly around handling congestion. In a single rack, it's one hop away. You're not really going to see as much congestion as you would in a scale out network, where you have multiple flows really competing for the same bandwidth across that scale out infrastructure. And again, with scale across is distance, right? Once you have distance, you're going outside the data center. You need encryption. You need to make sure that every flow that is going across your data center is not in your control. it's encrypted, and you also need to have like long distance technologies as well. So what data center speeds and feeds, like, going maybe up to 2 kilometers, more likely 500 meters, is not enough to carry you across your, data center sites.
Fascinating. And I guess when we're talking scale across and scale out, we're talking fiber rather than copper.
Scale across is always going to be fiber. You cannot go copper across the kilometers that you're looking for. In the case of scale out, you kind of have choices. The decision between copper and fiber is mostly going to be a toss-up between how much distance you need to go and the cost, right? And the speeds, by the way, we are talking about 400 gig, 800 gig. Copper is not going to be able to go more than 2-3 meter distances. So maybe from the server to your leaf switch, maybe copper can do the trick. But if you're going beyond 2 or 3 meters, you're definitely going to need fiber that is going to help carry you forward, right?
Okay, we've talked about AI for networks. And I think what we want to talk about here is networks for AI, i.e. what makes networking for AI workloads different from how we just sort of do networking in a normal data center?
Look, normal data center, what I call as your traditional general purpose enterprise data center running enterprise applications, even today is mostly done on 25 gig per server, right? And I've seen it be that way for the last 7-8 years. Nobody needs more bandwidth for your enterprise applications. Now, fast forward to the world of AI, and even back in, like, let's say 2023, 2024, with the Hopper class of GPUs, you are already looking at 400 gig per seconds of scale-out networking per GPU. And there are 8 of those GPUs. So you do the math, it goes into terabits per second per node. Fast forward to now, and that's driving 800 gig per GPU. So first of all, Michael, the bandwidth needs are insane, like insanely higher, right? And number two is that standard Ethernet was never designed to be lossless or congestion-free. It was always designed to be best effort. I'll get your packet from here to there. If I lose it, you're going to retransmit. That's the expectation, right? And enterprise applications don't feel the pain, right? Okay, the network retransmitted it, no big deal. If you start retransmitting packet, losing packets, or even dealing with a little bit of congestion in AI networks, you reach a situation where, if you're, let's say, training across 1,000 GPUs, any congestion could mean 1,000 GPUs are sitting idle. Because until all of them finish their piece of work, they cannot move to the next set of work to do, right? So that's not something you want from your expensive infrastructure.
Some of these GPUs, we're talking hundreds of thousands of dollars, right?
An 8-way system can be roughly $400,000 just for one node. It's easily millions and tens of millions of dollars of GPUs.
So you don't want your network to be a bottleneck, basically.
You don't want your network to slow that down, yeah.
It's interesting you talked about Ethernet, because Ethernet's been around for decades at this point.
Yeah, of course. Before I was born, maybe.
So it sort of feels like this strange juxtaposition between this brand new thing, AI, and we're using Ethernet. Sort of little old Ethernet.
There is a clamoring for more open standard Ethernet solutions because people know how to manage and operate those. So Ethernet has been picking up like a dramatic way in the last 2-3 years for that AI interconnect as well. And it's not the standard Ethernet. Like Ethernet was not built to be congestion free. Ethernet was built to be best effort. But over the last 2-3 years, vendors, including HP, Juniper, have put in a lot of investment to make Ethernet up-leveled to be able to meet the performance needs and congestion-free needs for AI workloads.
Right, and I guess organizations have really got skills within Ethernet.
Yeah, exactly. They're using Ethernet everywhere, in your campus, your branch, your WAN, everywhere else.
So how do you ensure that latency is low enough?
Yeah, so making it low latency is all about making it congestion-free. So think of it this way. If you have a 4-lane highway, and the 4-lane highway suddenly becomes a 2-lane highway, that creates a backup, and that's latency, that's congestion, however you want to call it, right? So the way we build Ethernet networks, first and foremost, is you never have that 4-lane highway going into a 2-lane highway. It's called a dawn-blocking architecture, where if it's 400 gig coming in, it has to be 400 gig going out the other way. That's a start, right? Ethernet can still cause congestion if 2 400 gig flows come in and they're trying to map to the same 400 gig link, right? And that was the problem with standard Ethernet or best effort Ethernet. But some of the technologies that we have introduced over the last couple of years is these switches are now able to look at the congestion in real time, in microseconds, monitor the congestion of the lanes. And if a new car comes in, I can see that this lane has 5 cars and this lane has 1 car. Let me send this next car that comes in down the lane that has fewer cars or lesser congestion. packets instead of cars from that perspective, right? So eliminating congestion is the same as eliminating latency or reducing significantly latency. Yeah.
When we've talked about sort of AI data centers or AI compute, liquid cooling comes in. Liquid cooling is always part of the conversation. Are we starting to liquid cool networking infrastructure now?
Oh, yeah, absolutely. The next question you might ask is it needed? Look, it's not technology-wise, it is not needed. The question is whether you need it or whether you want it. You can still air cool it. But if you're building a data center, you want your switching infrastructure to be liquid cooled a lot. The biggest constraint in a data center is power, right? So even shaving off 25% power on a switch, and you have thousands of those switches in your data center, could be a few kilowatts worth of power. Maybe you can use that and put more GPUs on your infrastructure and monetize that. And frankly, most of the new data centers that are being built out just specifically for AI or just specifically for GPU, they already have a liquid cooling infrastructure for the GPU rack. So then it becomes a matter of, is air cooling actually going to be harder because now I need a rear door heat exchanger or I need a more expensive cooling infrastructure that is running at more velocity. So what you're finding is that as people go build out new AI data centers that are already liquid cool enabled, it's actually more easier to have your switching rack also be liquid cooled. Then I don't have to have two different systems, one for my GPU rack and one for my, networking rack.
So looking forward, do you see networks continuing to adapt as AI workloads increase?
For as long as GPUs are evolving and requiring more and more speed, I think the technology is going to adapt very fast, right? We just talked about a lot about scale-out networking today, but scale-up networking, and it is just getting started. This is a constantly moving space, in my opinion, for the next few years.
Is there a limit to how much data we can transfer? Or actually, the sky's the limit at the moment?
Maybe like 7, 8, 9 years ago, we were at 12 nanometer fabrication technology, and everybody started to say Moore's law has ended. We need a completely new technology paradigm before we can scale this up. Guess what? Last generation was 5 nanometer, and now our 1.6T chips, we are going to be looking at 3 nanometer technology. Whether that goes to 2 and 1 and, sub 1 nanometer technology, it doesn't seem to end. But I'm not the expert on that topic, on the chip fabrication technology. But as long as chips can be fabricated at more minute granularity or more minute dimensions, it seems like sky is the limit for now, at least to me. Yeah.
Praful, thank you so much for joining us on Technology Now. I really appreciate it.
Yeah, thank you, Michael. Thank you for having me here.
Wow, that was a pretty interesting interview. Okay, one of the things that really helped me in the discussion to better understand everything was sort of the car analogy that Praful offered up about congestion in the highways and then treating some of the packets like cars and how they view everything. I wonder how much overlap there is between the way that network engineers think about networks and actual road engineers think about the development.
That's such a good point. It really helped me to understand when he just talked about why these networks need to be so fast. And actually why it can't just be handled with, standard data center switches. What he said was, congestion means that GPUs sit idle and you're essentially wasting a resource, a very, very expensive resource, $400,000 for a single node. So you sort of understand actually the congestion from a networking perspective. You don't want that. You want to make sure your GPUs are being used. What did you think about scale up, scale out, and scale across? Had you heard that before?
I feel like I had heard scale up, but I had not heard of scale out and scale across. The scale across thing was kind of interesting to me, seeing how far they're trying to scale the GPUs into multiple locations and whatnot. I especially appreciated learning why copper can't be used as well, because I obviously heard of this and I've heard of fiber optic cables and things for cable television, I guess. But I didn't realize how limited copper is, 2 to 3 meters. That's very short.
It's all in perspective, right? I'm currently talking to you over copper that's more than 2 or 3 meters because I live in the deep, dark countryside. So you can use copper, but again, it's for the sheer speeds and the sheer amount of throughput that these networks require means that, you have to use fiber for anything more than 2 or 3 meters, which is slightly insane. What I found really interesting was that the conversation about scale across and how actually the biggest constraint, I think is what Praful said, and I think we've heard this in other shows, is power is one of the main constraints when it comes to AI data centers. And actually, if you can spread AI workloads across multiple data centers, the sort of power constraints can be moved around a little bit. Again, liquid cooling. We have talked about liquid cooling quite a lot.
Yeah. because it comes up so much, I'm starting to get more and more of a picture of just how much liquid cooling is going to be used in the future. I mean, it already is used quite a bit, but then also even going back to some of the previous conversations about sustainability and being able to use liquid cooling to like be part of how you absorb some of this heat and then powering different like places where these data centers are housed. It's just crazy to me. I think as these scale out networks keep building up, since he said that this is kind of a newer area, we'll see a lot more liquid cooling with these different data centers where they need to use the scale-up networking architecture. So this is kind of exciting. It feels like we're watching something come to life.
Yeah, I would agree with you. Now, Sam, obviously, we've talked a lot about data centers in this episode, but it's not just organizations that use them. Pretty much all of us interact with networks in our daily lives in some manner. So something I really wanted to ask Praful about was whether our organizations and us as consumers would see these AI networking advances trickle down to, our normal data centers, networks, and maybe even us as consumers in our home networks.
Will Michael get 1.6 terabits at home, right?
Will I get this is what I want to know. Will I get 1.6 terabits?
That's the whole reason for this show, isn't it? No, I don't think so. I don't think that's happening. I don't think there's a need for it. And like I said, at general purpose data centers as well, it's still 25 gig, going to 50 gig, maybe going to 100 gig. So I don't see that, need for putting those high-speed technologies for general purpose data centers. But look at consumers, our lives are already getting impacted. So I think as consumers, GPUs are getting more powerful, the networking alongside is getting more powerful. So I think we are seeing the benefits of it. But we're not getting 3.2 or 1.6 terabits to the home, for sure, yeah.
Okay, that brings us to the end of Technology Now for this week. Thank you so much to our guest, Praful Lalchandani, and of course, to our listeners. Thank you so much for joining us. If you want to hear more about networking, we've also linked in the show notes to our episode with Rami Rahim, the leader of HP Networking.
And if you've enjoyed this episode, please do let us know. Rate and review us wherever you listen to episodes. And if you want to get in contact with us, send us an email to technologynow@hp.com. Sam, subject line.
Scale up, out, and across.
Ooh, nice. Like that one. And don't forget to subscribe so you can listen first every week. Technology Now is hosted by Sam, Jarrell, and myself, Michael Bird. And this episode was produced by Harry Lampert and Izzy Clark, with production support from Alicia Kempson-Taylor, Becky Bird, Alyssa Mitri, and Renee Edwards.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green. And our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a Fresh Air production for Hewlett Packard Enterprise. We'll see you at the same time, the same place next week.
Bye, y'all.
Cheers.